a recent paper that Peder and I did. So this is joint work with Peder, Bergh, and Peder Thompson, and it's about asymptotic vanishing of cohomology in triangulated categories. So I thought the first thing I would do is kind of give the motivation for where this came from. And actually, well, according to me, this is the motivation. It all started with this paper by Maurice Auslander in 1961, where he proved that over an unramified regular local ring, if you took two finitely generated modules over that ring, and if some Tor vanished, some positive Tor vanished, was equal to 0, then all the subsequent Tors are also 0. And this became known as rigidity of Tor, and it had a lot of implications and a lot of equivalences with other homological conjectures and things that Hochster has a great monograph where he kind of puts all these together with the direct summa and conjecture and the new intersection theorem and all these things. Anyway, this was a topic of great interest for a long time. And of course, people were interested in how can this be generalized? So for example, a few years after Auslander published that paper, I guess he posed that question in the paper itself. What if it was a ramified regular local ring? I'm not going to go into the definition of ramified and unramified, but um, what if it was a ramified regular local ring? Is the same thing true? And that was proved by Lichtenbaum a few years later. So this was known then for all regular local rings, this rigidity of Tor. And of course, people ask, well, what if it's not a regular ring? For example, what if it was a hypersurface ring, which is in some sense, the next best thing to being regular? And well, there's pretty easy counterexamples to this over a hypersurface. So you needed some extra hypothesis. And so one possible hypothesis was, well, let's assume since everything over a regular local ring has finite projective dimension, let's assume that one of the modules has finite projective dimension. Then is the rigidity of Tor still true? And actually, that conjecture was around, or I don't know if it's conjecture, but a question was around for a long time until 1994. About Ray Heitman gave a counterexample that no, you can have a module with finite projective dimension and any other module, well, and some Tor will be 0, but the next Tor will not be 0. Anyway, then you could ask the question, what if both modules had finite projective dimension? Does rigidity of Tor hold for those modules? And that's actually still open. And Ray Heitman, he was my postdoctoral advisor, and we worked on that question for a while, and it's proved to be pretty difficult. So it's still open. We don't know about it. Okay, so anyway, you could still look at hypersurfaces. You could still look at maybe say something about rigidity of Tor, or rigidity or vanishing of Tor over complete over hypersurfaces, and more generally over complete intersections, and why Tor, why not, what about X, and questions about vanishing X over regular rings or complete intersections, and basically that's kind of So you're wondering what does this have to do with triangulated categories? Well, yeah, it really this is the starting point. So anyway, let me it'll I'm doing the weave, I'm weaving the conversation. So eventually we'll tie this together. So anyway, for the talk, I'm going to let T denote a triangulated category, and something happened to my Y on category. I just noticed that. Sorry. And sigma, that's the shift, the shift functor, the endo functor. And so T is an additive category with the sigma endo functor, and then we have the class of distinguished triangles. And the cohomology we're going to be talking about then is just these Hom sets, these Hom groups, where you take the morphisms from X to shift IY. And I'm going to set, when I write Hom with the star there, I just mean that's the direct sum of all the Homs with ice shift. Okay, so that's the notation. Now, let's see here. I unfortunately can't see my banner because of the Zoom stuff. But anyway, is there a way to hide that? Anyway, yeah. So I want to focus on special types of triangulated categories. These are the ones that I call A-linear. So what is A? So I'm assuming A is a Noetherian graded commutative ring, non-negatively graded. And I'm going to be assuming that our triangulated category is what I call A-linear. And so basically, in sum, that means that these Homs, the direct sums of all the Homs, the Hom star of X and Y, is actually a graded module, a graded A module for all objects X and Y in the category. So what does that actually mean? Maybe I'll be a little more specific. So what that actually means is if you consider the graded center of the triangulated category, that's what I'm denoting by Z of T. So this is just the direct sum of all the degree I pieces of the center, where what is the degree I piece? It's just all the natural transformations from the identity functor to the I shift functor that commute such that the shift in the natural transformation commute up to sign. So that's what each degree I piece of the center is. And so take the direct sum of all those, that's the graded center of your triangulated category. And it turns out that this direct sum of all the Homs, the Hom star, X and Y, turns out to be a graded left or right module over that center. Oh, so I should point out that that center is a graded commutative ring, and these Hom stars become graded modules left or right over that graded center. And then we say that A acts centrally on the triangulated category T if there exists a graded ring homomorphism from that graded commutative ring A into the graded center. So through this homomorphism phi, the Hom stars are become left or right A modules. Okay. So that's what I mean by alinear. You have such a graded ring homomorphism. And you might be thinking this is kind of a crazy assumption, but it turns out it's not crazy. That this happens in a lot of cases, and we'll discuss those later in the talk. Okay, so we have an alinear triangulated category, and I want to make some assumptions now. So my Hom star, this is a graded module now over this graded commutative Noetherian ring A. By the way, I should mention that part of the structure, I said left or right. Well, it turns out that it's really, you can multiply either on the left or the right, and they're equal up to sign. So you can choose whether you want to think of these as left or right modules. Anyway, I want to assume that so here I write Hom plus instead of Hom star. So that means I'm just taking the positive half of the Hom star. So this is for, I greater than or equal to 0. So you remember Hom star is the Homs from X to shift I, Y. So I just want to take the part where the I on the shift is greater than or equal to 0. So the positive side of the Hom star module. And I want to assume that that's finitely generated over this graded commutative ring A. And very quickly, I'm going to get rid of the graded commutative assumption and just assume that it's commutative. So that's the next assumption here is I'm going to assume that actually A is generated by its degree D part, where D is even. So it's generated as an algebra over its degree D component over the 0th degree over A0, and assume that D is even. Now, you may be wondering why we do this. Well, in practice, we're not, this, I mean, in the applications, this graded commutative ring A can be generated in different degrees. It can, it's Noetherian, so it's got a finite generating set as an algebra over A0, but those generators can exist in different degrees. And so what one can do is kind of replace the original A by a subalgebra generated by powers of those generators, so that all the powers now have the same degree. And if it's not even so basically D is what is the least common multiple of the degrees of the generators. And if it happened not to be even, well, you just double it and make it even. And when the Hom star was finitely generated over the original A, it's still finitely generated over the subalgebra. And the point being, now we have a subalgebra that's commutative and generated all generators in the same degree. So this allows us to, do some commutative algebra is basically the point. Okay. So those are the assumptions. Here's the theorem. Asymptotic vanishing of cohomology in alinear triangulated categories. That's the point. So this is a theorem of mine and Peder. And assume either that these HOMs from X to shift IY have finite length over A0 for all sufficiently large I, or assume that the 0th degree component of A0 contains an infinite field or is local with infinite residue field, either of these two assumptions. Then the conclusion is, this is the asymptotic vanishing part, the conclusion is there exists an integer n with the following property. If the HOM x into shift niy is 0 for a complete set of residues n1 through nd greater than or equal to n, so a complete set of residues mod d, then in fact all of the HOMs vanish. The HOM x shift iy vanish for all I greater than or equal to n. Okay. So I don't know if that's clear, but so for example, if the D happened to be 2, what this theorem would be saying is that there's some point after which, if you have an odd HOM vanishing equaling 0 and an even HOM equaling 0, then in fact all the rest of the HOMs have to be 0 beyond that point. Okay. So I'll mention a little bit about the proof of this. So the proof under the assumption 1 is, well, first of all, you have this graded module. No, I'm taking the HOM plus, so this isn't the non-negatively graded module. It's a module over an algebra generated in degree D. So therefore, it naturally decomposes as a direct sum of D submodules. So you have all the submodules with index congruent to 0 mod D, all the submodules with index congruent to 1 mod D, etc. These all form, I say the HOM plus is a direct sum of all these submodules. Okay. And so I'm calling those submodules H sub I. Each of these submodules is finitely generated over A still. And so what you have is a finitely generated module over a commutative ring. And here we're assuming, and this is the proof of 1, so we're assuming that these HOMs all have finite length over A0. So, the standard result from commutative algebra says that, you get a Hilbert polynomial. So this is actually first proved by Hilbert, right? That there exists polynomials that tell you what the length is, for sufficiently high degree. So, but since we have D submodules, we're going to have D Hilbert polynomials. That's what I'm calling PI. So for each I, the PI of n just tells me the length of the dn plus I HOM. Okay, and this is for all sufficiently large n. So now we have these Hilbert polynomials, and if they happen to all be the 0 polynomial, well, where there's nothing to do, so we can go home. But if they're not all the zero polynomial, then we can choose an n beyond any of the zeros of those PIs. And therefore the hypothesis and conclusion of the theorem hold. Okay. So in this case, yeah, it's proved just using the fact that you have these Hilbert polynomials. Okay. In the second case, well, the same thing. The Hom plus decomposes as a direct sum of D submodules. And again, each of those submodules is finitely generated over your commutative algebra A. And in this case, because of that infinite residue field or subfield in either case, you can use a standard prime avoidance argument to prove that there's an element. Actually, you can assume it's a degree D element, A, that's a non-zero divisor on each of those submodules for sufficiently high degree. Okay. And so in this case, you have this non-zero divisor on the tails of all these of these D submodules. Therefore, at some point, you can't have any zeros. Otherwise, it would contradict the fact that A is a non-zero divisor. So again, the hypothesis and conclusion of the theorem hold in this case. Now, I was, yeah, well, right. So yeah, in either assumption 1 or 2, it's basically just standard commutative algebra that gives you the results. Now, it occurred to me that maybe there's a better statement of the theorem, because what's really happening, right, is that if there's well, let me just read the statement. Perhaps a better statement of the theorem would be that if there exists an integer n, there exists an integer n with the following property. If the Hom from x to shift iy is non-zero for some I greater than this integer n, then in fact all of the Homs of that parity have to be non-zero beyond that n. So I don't know which statement is better, but anyway. So this is what we mean by asymptotic vanishing. There's the behavior can't be erratic at infinity of the vanishing of a cohomology. Okay, so what I want to do now is give some applications of the theorem. So the first application is for complete intersections. Okay, so this is kind of what I was saying at the beginning. One can be interested in vanishing Tor over regular rings or hypersurfaces, or more generally complete intersections, and similarly X. And so now we're talking about cohomology over a complete intersection. But anyway, I don't know. I thought I'd just review what the definition of complete intersection is. So if we have regular local ring Q and sequence of elements in Q that form a Q regular sequence, and we quotient out the ideal generated by that, then that's what we call a complete intersection. So what is a regular sequence? So that just means that the first element in the sequence F1 is a non-zero divisor on Q, and then the next element in the sequence F2 would be a non-zero divisor on Q mod F1, and continue. So FC would be a non-zero divisor mod the previous Fs. And so any quotient by that regular sequence where Q is regular, that's called a complete intersection. And by the way, where does the name come from? It just comes from the fact that when this is the case, the Kroll dimension of R is the Kroll dimension of Q minus C. So if you think about it, kind of, it's a geometric term, right? It just means that when you're taking the hypersurfaces defined by these Fs, that they intersect, as completely as possible. So each time you're reducing the codimension. Anyway, that's where the name comes from. So anyway, I'm looking at a complete intersection now, which is in some sense, not regular, but close, maybe close to being regular. Okay. So a corollary of the main theorem then is if intersection and M and N are finitely generated R modules, then there exists an integer n with the following property. If x I is equal to 0 for some even I and some odd I greater than or equal to n, then in fact all the x must vanish for I greater than or equal to n. Okay. So this, this theorem was already known, but was it? Yeah, I think so. Yeah, but anyway, it's a corollary of the main theorem. So how does the proof go? Well, so what you can do is if your original complete intersection R for some reason didn't contain an infinite field or didn't have an infinite residue field, then you can always go to a faithfully flat extension where that is the case. So that's kind of the first reduction. So you move to a different complete intersection that does have an infinite residue field or contains an infinite field. And then you look at the bounded derived category of the complete intersection R. Okay. So this is the triangulated category. And in fact, it's alinear, where in this case, A is a polynomial ring with coefficients in R, the complete intersection, a polynomial ring in C variables, and each of them having degree 2. So this is what's typically called the ring of cohomology operators, or maybe Eisenbutt operators. But anyway, yes, the bounded derived category over the complete intersection is an alinear triangulated category. And each of those variables having degree 2 means that in the theorem, the D is 2. You could choose D to be 2. Which is why the statement of the corollary is even and odd, because D is 2 in this case. Yeah, and the Hom plus is finitely generated over this ring, and in this case, of course, the ext I of M and N is is just the Hom. Well, I suppose actually you could, in the derived category, you can replace M and N by their free resolutions. But anyway, the X here is just the cohomology in the triangulated category. So that's the proof in this case. We also have, let's see, another corollary. In this application, we're talking about finite dimensional algebras. So let R be a finite dimensional algebra over a field in M and N finitely generated R modules with finitely generated cohomology. And I put a little dagger there just to remind me that, oh, that's an assumption. Doesn't all, okay, so for complete intersections, you always have that the Hom plus is finitely generated over this ring of cohomology operators. But in the finite dimensional algebra case, that's not always the case, that the Hom pluses are finitely generated over some algebra, but it happens in a lot of cases. So that's an assumption. I just wanted to point that out. Okay, then conclusion is there exists integers d and n with the following property. If the nth x of m and n is 0 for a complete set of residues n1 through nd greater than or equal to n modulo d, then all the higher x's are also 0. Okay. So proof in this case, yeah, the bounded derived category is triangulated. So that's what you go to the bounded derived category of this finite dimensional algebra. And this is an alinear triangulated category where in this case, you can take A to be the Hochschild cohomology ring. And so we're assuming that the Hom plus is finitely generated over the Hochschild cohomology ring. This happens sometimes. And in this case, again, the X is just the cohomology of the triangulated category. So the theorem applies to these cases of finite dimensional modules over finite dimensional algebras. Third application, which is the application to group algebras. So here, G is a finite group and R is the group algebra over a field K whose characteristic divides the order of the group. So it's a modular group algebra. And M and N are finitely generated R modules. Then same conclusion as the previous corollary, there exists integers d and n with the following property. If the nth x's are 0 for a complete set of residues n1 through nd greater than or equal to n modulo d, then all the higher x's are 0. Okay. Proof in this case, here we take the stable module category of this group algebra. So that's a triangulated category. It happens to be alinear. In this case, where A is the cohomology ring, XKK. And the Hom plus is finitely generated over this cohomology, the cohomology ring, and the x to I in this case is just the stable Homs from M to shift minus IN. So again, it's just a straightforward application of the main theorem. Okay. Well, that's basically the program. I had one specific example I could illustrate for the last application. So for a group, the group S8, so this is the symmetric group on 8 letters, and just take the field to be the field of 2 elements, F2. Then it turns out that the cohomology ring in this case, pardon me, is generated as an algebra over K by elements of degree 1, 2, 3, 4, 5, 6, and 7. So this is a result of the list of reference here at the bottom. So this is not our result. It's just an illustration of the fact that your algebra A can in fact have generators in different degrees. And so in this particular case, if you took the LCM, of those, you get 420. So the application of the main theorem to this case, your D would be 420. Anyway, just an illustration of what can happen. Yeah, so for the last slide here, I just would mention that for future work, well, really ongoing work, we're exploring a theory of multiplicity, actually, in triangulated categories. So again, multiplicity is a standard topic from commutative algebra, and since we have a commutative ring and our triangulated categories are alinear over this commutative ring, then we can attach invariance to these HOMs, right? Namely the multiplicity, and study properties of that multiplicity. And so one thing relevant here is that yeah, we can define a multiplicity for pairs of objects in an alinear triangulated category, and get applications, for example, where if this multiplicity vanishes, is 0, then kind of just broadly speaking, then if you have half vanishing of the HOM plus, if half of the HOM plus vanishes, then the other half has to vanish too. So that's kind of a vague statement, but just to illustrate that the multiplicity also has something to do with vanishing cohomology in this case. Anyway, that's basically all I wanted to say. So thank you.
Thank you, David. Can we all please unmute ourselves and give the speaker a round of applause? If you have any questions for David, please ask them now.
So I have a question. So in your main theorems, and also in the applications, of course, there was a D and an N. So I think I remember the D. This was just the degree in which the algebra was generated. But the N, how did you find the N? I forgot.
Well, that's a good question. So the N is in the first case, there was two different assumptions. One was on, the HOMs having finite length. In this case, you get Hilbert polynomials.
Right.
Right. And so these are polynomials with rational coefficients. And if they're, non-zero, they only have finitely many roots.
Right.
So the n is chosen to be greater than any of the roots of those polynomials.
Okay.
Yeah.
Okay, so this is how you find explicitly
Yeah.
like in case
you know,
in case
of course
one.
yeah, of course you can
Okay.
cook up modules of the Hilbert polynomial with roots as far out as you want. So there's really no way to bound that n. I mean, that's a big, a well-studied problem in commutative algebra, you know. Can you ever bound that n? And in the second case, you're talking about a prime avoidance argument, where you basically just know that something's not contained in the union of primes, and there's again what degree this non-zero divisor sits in, it exists, but in what degree it sits in, who knows? So that's the n. That's the n in that case. And again, that's a major problem in commutative algebra is how to bound that, and it's in general you can't. So that's, I guess, really the heart of the term asymptotic, is that we really don't know in general what that n can be, but we just know it exists.
Thank you, Andrew. Any other questions? The group cohomology, you had a corollary involving X over group algebras of finite groups. Is that a new result, or was that known before in the group cohomology literature?
I'm actually not sure.
It looks like the kind of thing that should be hidden in Benson's books somewhere.
Yeah, maybe.
Okay.
I'm actually not sure if it's written down anywhere. I don't know. It might be known, but I don't know. Maybe not written.
And I had a comment. So I think the group algebra case, you can do it more generally now for finite flat group schemes over a Noetherian basis. So it is now known that the group cohomology in that case is still a finitely generated Noetherian ring algebra. And there is an analog of the stable module category in that setup. So like the same argument, I think, will show the same
What was that?
inclusion with the X groups.
What was that setup again?
I'm sorry?
What was the setup again you said?
R is a Noetherian commutative ring, and G is a finite flat group scheme.
Okay.
So there's a paper by Wilbert van der Kallen from, I think it was published last year, but it was archived the year before, which shows that the group cohomology is a Noetherian, like finitely generated algebra.
Okay.
Generalizing the Friedlander-Suslin theorem, which was known for fields. And the analog for the stable category, I think it's in a paper by Toby Barthel and BIKP. So BIKP would be Dave Benson, Srikant Iyengar, Henning Krause, and Julia Pevsova. And the analog of the stable category, I think they write it RE rep GR. Yeah, I think it's the same proof should go through, unless there is a technical trap somewhere. Yeah, sorry.
Could I ask a question? So you have like a finite length assumption on the eventual modules, but is that like something you 100% need, or do you have counterexamples where it doesn't?
To the modules being finitely generated?
Oh, finite length. I thought you wanted was I wrong about that? I thought you assumed you had finite length modules in high degree.
Yeah.
Is that something you need, or does that just make the proof go through? I mean, are there examples?
Well, I don't know how else to. I mean, for that hypothesis, right? We're getting these Hilbert polynomials. So I don't. You mean that maybe you could assume that you had another invariant or something that.
No. I was just asking like if there are examples where you just have finitely generated in each degree and maybe you have the vanishing conditions, but they don't imply the rigidity like you had. I was just curious like to if you thought it might hold more generally. Just
I haven't really thought about it. I mean, I don't know if you just assume that it's finitely generated in each degree. I don't know that you would get a Hilbert polynomial from that. I'm not sure. Yeah, I haven't really thought about it yet.
Thank you, Josh. Any other questions, anyone? Right, if we don't have any more questions, let's thank David once again. If you can share the slides with me afterwards, that would be great.
Okay.
Because sometimes people ask for them. Right, yeah, thank you all for coming. We have Emanuele Macri from Paris next week. Hopefully, I'll see some of you there. Bye-bye.